All right, thank you. Yeah, so today I'm going to talk a bit about NMDA receptor pharmacology, some of the work done in my lab, as well as kind of my opinions of some of the other work done in the field, and some things, kind of pitfalls I have. And I can tend to be a bit of an iconoclast, nothing personal if you're annoyed by it, but I think we need to be critical in this field, and it's really important to question some things. So hopefully you'll find it interesting. I kind of scaled back the SAR. I just did an ACS, American Chemical Society talk, and it was heavy on the SAR. I think I'll spare you some of that. Great. So as promised, some of my disclosures, consulting and research funding. All right. So, I want to talk a bit first about the history of dissociative drugs. The sort of start of this was the serendipitous discovery of PCP at Park Davis by a chemist there, Victor Harold Maddox, in 1956. And really, if it wasn't for this discovery, we probably wouldn't be here right now. So we should be very thankful for him and for following up on an obscure observation he made about a reaction not working. The term dissociative drugs comes from the phrase dissociative anesthesia, which was coined by Toni Domino, the wife of a very famous and recently deceased ketamine researcher, Edward Domino, and PCP researcher. And the idea was that the patients were dissociated from the environment. They almost seemed cataleptic. You disconnect the mind from the sensory input. And their early ideas were that this sort of limbic, gating, cortical disconnect. And some of the hypotheses even today share some similarity with that original idea. Examples of dissociative drugs, of course, are PCP, ketamine, and dextromethorphan. I'll talk about some others. My lab has also been very interested in research chemicals, or legal highs. And the reason being, there are a lot of these. In fact, more of these than there are clinically approved NMDA receptor antagonists. And although it's anecdotal evidence for the most part, we can learn a lot by studying reports of people taking these about potencies, interesting pharmacological effects. And there's also often kinetic data, toxicology data in the medical literature as well, which we also contribute to. So this is the NMDA receptor. I'll talk a little bit about that. It has this transmembrane domain that sits in the cell membrane. Then there's a ligand binding domain, which glutamate and glycine bind to, and then an amino terminal domain which some other interesting drugs are able to bind at. So NMDA has been hypothesized to underlie the major therapeutic, dissociative, and hallucinogenic effects of dissociative drugs. There's weaker evidence for the therapeutic, and as you know, there are many hypotheses to explain the antidepressant actions of ketamine. I still think NMDA is the #1 contender. And or at the very least, has not been adequately ruled out. And so I'll discuss that a little bit. The evidence for NMDA mediating the dissociative effects is incredibly strong. I'm not going to go over it today, but I've written about this. I think it's very difficult to argue with. All the other hypotheses, like the sigma receptors, have more or less fallen. And NMDA is the only one left standing. And a good hypothesis is one that has yet to be disproven. You never prove a hypothesis. The other thing is, even though some of these drugs are selective, although many of them are not for NMDA, that doesn't simplify what's happening, right? If you interact with the NMDA receptor and inhibit it, you get very complex downstream effects because the brain is so interconnected. Virtually every single neurotransmitter system we have bothered to look at after giving ketamine is affected when you give ketamine. I mean, anything. Pick your favorite, go online, you will see ketamine affects every neurotransmitter system. And that's fascinating. It also makes our job difficult to figure out mechanism of action. The other problem is every other psychoactive drug, for the most part, does this. And so figuring out this signal to noise, which is something I'm going to talk about, is so challenging in the CNS space. And I think is why we have such high rates of drug failure. The first class of compounds I want to talk about are the channel blockers, represented by ketamine and PCP. So again, if you remember the NMDA receptor, they bind in this transmembrane domain inside the ion channel part. So normally the NMDA receptor opens and sodium and calcium can flow into the cell, potassium out. These channel blockers come in and actually physically block that channel, preventing ion conductance. So the other thing that I think is really important to point out before I get too far is that often we talk about NMDA receptors as if it's a single thing. And even in the lab, sometimes we study it. I'll show you binding we've done, that we kind of treat it as if it's one entity. It's not. It's a tetramer protein made up of 4 subunits. And you can pick from 3 different families of subunits, NR1, NR2, and NR3 families, to make a functional NMDA receptor. And there's some limits. Nature has put some limits on the stoichiometry, the ways in which we can combine them. But regardless, and it gets a little complicated mathematically how you define a difference, but there are tens, if not thousands, of distinct NMDA receptors in the brain, which is insane. And again, you can say something selective for NMDA receptors, but which NMDA receptors? There's no lab on Earth I'm aware of that has even the constructs to make all of these, to study them. It's very difficult to study many of them in the brain just because of the limitations of experimental techniques. So there is a whole lot we still don't know. Interestingly, ketamine shows some selectivity when looked at in a subset of these channels for those specific type called homodimers, which contain NR2C subunits, and to a lesser extent, NR2D. And that's really interesting and promising. It's been proposed to maybe underlie the selectivity of ketamine and some other channel blockers for GABAergic interneurons, and that might be why they're able to elevate glutamate. But there's still a lot we don't know. Okay, so just quickly, a little more history on PCP. So again, it was discovered in 1956. It was marketed soon thereafter. Regulatory processes were very different then as a general anesthetic, but it was soon discontinued and replaced by ketamine, which had better pharmacokinetic properties. Patients would come out of anesthesia and be, dissociated and hallucinating for hours on end. Whereas with ketamine, half-life's really short and they're out fast. The street use or non-medical use of PCP started very shortly after its introduction and continues to this day in the United States. Interestingly, it's not prevalent really anywhere in the world other than the United States. The other fascinating thing is a lot of analogs of PCP appeared on these illicit markets, particularly between the late 1960s and 2000s. And they kind of disappeared. Today, you don't see that at all. But what you do see is an extensive number of these sold on the internet as legal highs or research chemicals. There's probably something like 30 now. And again, my lab is very interested in studying these. But one sort of side effect of doing research in this field is some of your drugs end up being sold as research chemicals. And so I'm in a position now where I'm studying drugs that I made, with my dissertation that are now being sold online. So that's interesting. This I just think is funny. There was a lot of hysteria in the United States about PCP, and law enforcement was terrified. They thought literally people turned into the Incredible Hulk. The taser was really developed in large part to immobilize people on PCP. It was like optimized for people on PCP, and companies sold nets to capture people on PCP. There are reports in the literature of people ripping handcuffs, like no problem, ripping patrol doors off of car doors off of patrol cars. I mean, law enforcement was terrified of people on PCP. And of course, the evidence is, as you might expect, very suspect that any of this was related to PCP. And a wonderful movie about the dangers of PCP, what one hit will do, is Death Drug. So I recommend checking that out. All right. So moving on, we have ketamine discovered by another Parke Davis individual, in this case, a consultant named Calvin Stevens in 1962. Very soon thereafter, approved and marketed as a general anesthetic. And we all know that story, discovered ultimately to be a very effective antidepressant drug and approved with Spravato most recently, although the racemic ketamine is widely used off-label. Ketamine, of course, is racemic, as you know, and there's a right and left-handed form, an R and S form. The S is about 4 times more potent at inhibiting NMDA receptors, but R also inhibits NMDA receptors. And one of the sort of iconoclast things I want to point out is there's a lot of literature coming out showing the difference between R and S ketamine these days. But a major problem with it is they're comparing the same dose of R and S ketamine, often 10 mg per kg. And the problem with that is, for some cases that might be fine, but if you really want to see if the drugs in fact can do different things, that's not dose dependent, you have to do a full dose response. And in a lot of the older literature where they did full dose responses, in pretty much every assay, they are identical. It's just that R ketamine is shifted in this dose response and is less potent. Now, of course, I'm not saying there are no differences. That would be ridiculous. But for the most part, a lot of the newer research, I think, is highly biased. It would be like doing a comparison of 2.5 milligrams of S-ketamine with 10 milligrams per kg of S-ketamine. Of course, you're going to find differences. And it's easy then to play up the differences as if they're profound. And unfortunately, you see that a lot. The other thing I want to point out is, there's a lot of this interest in R-ketamine, and I do think potentially R-ketamine will be an antidepressant, have antidepressant activity. However, I'm skeptical that it underlies the antidepressant effects of racemic ketamine. And I also am very skeptical that we will be able to achieve antidepressant doses without causing dissociation. And I will talk about this a little bit more, but if you look at the clinical literature, it's clear that S-ketamine and racemic ketamine do all of the same things. They have the exact same clinical profile in multiple randomized controlled placebo trials. You really don't see any differences, with the exception of S-ketamine. When you control for route and administration route, or route of administration, S-ketamine is more potent, which is what you would expect if it's the primary contributor to the antidepressant effects of racemic. I'm not saying that R doesn't contribute to racemic, but it's very hard to figure out how much is really left for it to explain. If you can explain almost all of its activity with S-ketamine, how much is R really contributing? That said, I still think it will work, just at higher doses, and I think you're going to see dissociative effects at those doses. People claim R-ketamine is not dissociative. That's absolutely not true. 100%, I promise you, it causes dissociative effects. I know multiple people have tried it without question. It's just 5 to 10 times less potent than S-ketamine, which is what you would expect from the literature. So a really cool study in Nature came out where they actually solved the binding mode of R and S-ketamine inside 2 different NMDA receptor subtypes. And this kind of confirmed a lot of work over the years of mutating residues to kind of predict where ketamine was binding, but now we can actually see it with these cryo-EM structures. And sure enough, it was right inside that channel, blocking the selectivity feature, selectivity pore for calcium. And you see it's in this vestibule region. So this is a really cool study, and they did like molecular dynamics. You can kind of see how it moves around in the binding site. And I would definitely check that out. And this is really useful for drug discovery because we can now do like docking studies and see, well, what if we add this to the molecule? How does that affect its binding? Can we engage this residue? You start doing really cool stuff like that. So the next class I want to talk about are the diarylethylamines. MK-1, interestingly, which is like the gold standard NMDA receptor antagonist, is a conformationally constrained diarylethylamine. And it's actually one of the most potent and selective, as far as we know, NMDA receptor antagonists. That's why it's so widely used. One of the main reasons it's so widely used in research. But there are a number of sort of unrigidified forms of MK-1, some of which are research chemicals like diphenidine and ephenidine. And then we have several clinical candidates, romacamide and lanansamine, which I don't know that I say right, but I've not heard anyone pronounce it over years. So anyway, the romacamide was actually tested in some neurodegenerative diseases and epilepsy, and did show some efficacy, although nothing impressive enough to warrant moving forward in the clinic. I think lanansamine is interesting because it sort of showed mixed results, but ultimately seemed like it did not have antidepressant activity at the doses used. And I just want to point out that the doses used did not cause dissociative effects. And I really think that's key. I'm not like, I think it's good to try drugs, NMDA receptor antagonists at non-dissociative doses. We should do that. But at this point, we've done that extensively. And the result is all of them have failed. The only approved NMDA receptor antagonist in depression is ketamine, and without question, it's causing dissociative effects at therapeutic doses. You can get finicky with the rating scales, but again, snort those doses of S-ketamine, and I don't care if the rating scale doesn't say it's dissociative. That without question, it's dissociative at those doses. The rating scales were not developed to assess that, but it feels like you drank a few beers and that I'm fine with calling that dissociation. So my kind of point here is what would happen if we tested this drug and some of the others at dissociative doses. If you really want to test the NMDA receptor hypothesis in depression, I think we have to use dissociative doses of these drugs, right? We know dissociation is correlated with NMDA receptor occupancy. It's very well understood. And I kind of see dissociation as a biomarker for predicting target engagement. Okay, I don't know which scale would be best. Maybe just asking, from 1 to 10 beers, how drunk do you feel? Like that might be fine rather than some of these other complicated scales. But I really can't emphasize that enough, because I'll show you just failure after failure with these drugs. And they all cause dissociative effects for the most part at high doses. And I don't think this is an exception. In fact, an analog of this, the N-ethyl analog, is being sold as a research chemical now. And all indications are that it's dissociative. So at higher doses, I'm sure it would, unless it has kinetic issues. And interestingly, one other thing, I'll probably skip over this, and I know this slide's busy, but this is some work we did with diphenidine and some other diarylethylamines. We found that an interesting thing about these compounds, if you're going to develop them clinically, there's a discrepancy between their potency in binding and functional inhibition in vitro and their potency in vivo. They're not very potent in humans, and we actually do not know why. We've been on and off trying to figure this out for a few years. It doesn't seem to be kinetics. There's some idea about pharmacodynamics with trapping in the channel. It doesn't seem to be that, but it's specific to this class of drugs, these diarylethylamines. So it's a very interesting topic. And what's really cool is in the rodent models we use, it's consistent with the human data. They're substantially less potent in rodents as well. So we think we can use the rodent models to maybe answer this question. So hopefully, in a year or two, I'll have more information. We'll see. All right, I think memantine is another interesting example of an NMDA receptor antagonist channel blocker. It's approved for moderate to severe AD, at least in the US and I believe other countries. It interestingly has about the same potency as ketamine at blocking the NMDA receptor. This is binding we did, ketamine in green, memantine in this diamond, and you can see these MK1 displacement curves are identical. The affinities are more or less identical. And another thing is, sometimes in the literature, people will say memantine's not dissociative. They're not a dissociative. Also, absolutely not true. There are extensive reports online of people taking 100 milligram doses of memantine, and without question, it's dissociative. One reason it's probably not used like non-medically or recreationally is because the half-life is so long. If you take memantine at a dissociative dose, you're going to be whacked out for a day or two. And I think that's one reason you would never want to use memantine in the way we use ketamine at dissociative doses for depression, right? You think 2 to 4 hours is bad to monitor patients? Just imagine 2 to 4 days. So that's kind of my hunch. And when you see the trials that have looked at memantine, it's the same potency as ketamine, right? Same binding, and actually the dose for milligram, it's similar potency. But the trials that have been done used low doses of memantine that are not really dissociating. And they, administered in a way that are different from what we do with ketamine in the ketamine trials. And, I think this is another bit of, sometimes I hear this as evidence against the NMDA receptor hypothesis. But again, if we gave ketamine at these doses, absolutely it would fail. We know that. We've done those trials to show the low doses of ketamine don't work. So again, I think to me, that's the most likely explanation still for all the failure of these other compounds. You're just not getting target engagement to the same extent we get with ketamine. And dissociation is actually probably a beautiful biomarker for looking at that target engagement. All right. Most recently, my lab's become interested, and we're just sort of very dipping our foot in these NR2B selective NMDA receptor antagonists. These are really cool. They don't bind inside the channel. They bind at a different site, but they have the same sort of end result, which is they inhibit the receptor. But they're able to target a specific subunit of NMDA receptors, the NR2B subunit. So they're selective for only certain NMDA receptors, okay? And what we did here was, this is, again, a binding experiment. You have different concentrations of these various drugs. And then you have radioactive MK1 here, and you're measuring the ability of the drug to displace the radioactive MK1. So you're competing for the binding site and displacing it. When you use drugs like memantine, ketamine, PCP, you see full displacement of MK1, meaning you're displacing it from all the different NMDA receptors in rat brain. But with ifemprodil, which only targets the NR2B, you see this sort of plateauing effect, where you're only displacing about 40% of the MK1 there, meaning, it's neat that about 40% of the NMDA receptors in our rat forebrains appear to be NR2B containing receptors. So I just think that's kind of neat that we're able to see this in just a standard competitive binding assay. And again, they don't compete for the same site, but what ifemprodil does is it binds up here in the amino terminal domain and changes the shape of the protein to lock this channel. And that prevents MK1 from getting on and binding. And it also obviously prevents the ion fluctuation through the channel. Just keep going back. Okay. A number of these NR2B antagonists have also been evaluated in human clinical research. This one, traxoprodil, is really interesting to me because it's one of the only ones, actually the only one I'm aware of, that did show decent efficacy in a phase 2 trial. What's really interesting about this, it was discontinued not for efficacy, but for QTc prolongation. But fascinatingly, and they gave this kind of IV, single dose, similar to the ketamine trial, there was dissociation in this trial. They actually had to back off the highest dose because they didn't want to cause dissociative effects. They kind of developed it as a non-dissociative drug and then realized, oh crap, it is causing dissociation. Let's back it off. But they did that like halfway through the trial. And so you did see efficacy with this. Even at the other doses, although they didn't meet the criteria on the dissociative rating scales, they do describe some of the effects. And it's, a general intoxication. So maybe it doesn't meet, again, the criteria on the dissociative rating scales, but people might still feel like they drank a few beers like you do with ketamine. So I think we need to be careful how we're assessing the dissociative effects in some of these trials when they're saying non-dissociative activity. Others of these NR2B antagonists have failed, and in those cases, there were no dissociative effects seen, which, again, this is just sort of more evidence to support my hypothesis that we at least haven't ruled out the NMDA receptor hypothesis because of these failures. I think the easiest way to explain it is we weren't achieving the same level of occupancy, the same NMDA inhibition that we're getting with effective doses of ketamine. Finally, we have the glycine site antagonists or partial agonists. These are probably the most complicated because of the partial agonism thing. What that means, sometimes these drugs are called like mixed agonist antagonists, and kind of they're like context dependent. In some cases, they can stimulate the receptor, and in other cases, they can inhibit. And that makes them complicated. So, I don't have time certainly to get into that complexity. An interesting one is D-cycloserine, probably the earliest report anyone's aware of in the literature of an NMDA receptor antagonist having an antidepressant effect is this report from 1959 by George Crane describing high doses of D-cycloserine in psychiatric patients showing an improvement in mood. So that's interesting. And there were signs of dissociative-like effects. Some of the patients had to be discontinued for exacerbation of psychosis and just general signs of impairment. So it's again very interesting. The other one I want to touch on is Repastinel, and that's because we have a lot to learn from Repastinel, I think, and we all need to take a critical look at this. In all of the preclinical assays that are done and are still the gold standard in depression, the synaptogenesis for swim, this stuff looked like the greatest thing since sliced bread. I mean, just synaptic spines like coming out of the field of the microscope field, growing out of the rat's ears and nose, like stuff was amazing. For swim, weeks later, the mice are just like, seriously, like it looked so good. And Allergan was so convinced they sunk $500 million into this, and at least, and it just one after the other after another, 3 phase 3 trials just completely flopped. So it's like, well, what is the issue? What's the problem here? And I think the issue, and this happened again with AV101, a similar drug just recently. I think the problems with the preclinical models. So I know I got like a minute or two left, real quick. So if you look at forced swim or tail suspension, you can do it with the same thing. People will say, oh, well, all antidepressant drugs and treatments are active in forced swim. So that's a good thing. It sounds like, wow, it's able to pick up all these mechanistically diverse antidepressant strategies. But if you look in the literature, literally every other psychoactive drug you can think of has been shown to be active in the forced swim test. Not only that, there's no like pharmacological consistency. It's a nightmare. You have agonists and antagonists at the same receptor, both being active in forced swim. To make it worse, in other cases, they block the action of other drugs in the forced swim. So you could almost come up with any hypothesis you want, just blindly pick two drugs, and you could use this test without question to support it. I actually want to propose a grant to NIH to do that. I think it would be awesome. Because I'm not kidding, almost you can. That's why every week a new study comes out of figuring out ketamine's mechanism. And I know it right away. Okay, forced swim. And sure enough, you know, it's just that. And there's so many of these, it's just ridiculous. And the psychedelic literature, the 2A, which I also do a lot of work in, it's now made its way over to there. My heart rate just every week, it's just horrible. And I think, you know, the same thing about synaptogenesis, right? Synaptogenesis is really fascinating. I think from a physiological standpoint, it's so interesting to look at. But you look in the literature, all psychoactive drugs affect synaptogenesis. And when you think about it, they should, right? Like, what does the brain do? It's this dynamic machine that changes its connectivity when you mess with it, right? So if you mess with it with different drugs, you'll get these same changes. My favorite example of that is cocaine. The cocaine literature, you could literally swap out the empirical data for the ketamine data and not tell the difference. BDNF, mTOR, rapamycin, blocks, all the same effects. But in the cocaine literature, it's not the antidepressant effect, it's the addictive potential of cocaine. And the drive to use lasts a week. And that's why you see these changes last a week. And it's just, there's empirical data, and then that's like hard science. And then there's the narrative, the philosophy, and that's humans. And that's that's the weakest link in science. We can come up with, any smart person can come up with these narratives that sound great. You get a Nature paper, a science paper, a grant, but you're not really getting at the root of the issue. And so I think we really need to include more like false positives in our work. You never see that, right? It's just ketamine. And whatever ketamine does, people can weave into their ongoing evolving hypothesis, right? But they're not showing, oh, cocaine does the exact same thing. Methylphenidate does the same thing. Nicotine does the same thing. Caffeine does the same thing. And so, you know, we just really, really, really need that degree of skepticism, I think, in our work. So I think, yeah, that's where I'll leave it. So.
Fantastic. Thank you very much, Jason. I think we've got time for a couple of questions because we started a bit late.
Sorry, but in your opinion, so do you need the dissociative effect to have an antidepressant effect? Because my understanding that a lot of studies show that even if you don't reach a dissociative effect, ketamine can have an antidepressant effect.
Yeah. So yeah, good question. Like, what's the relation with the dissociative effects and the antidepressant effects? So I think there's two parts to that question. So no, I don't think we have evidence to say it's necessary. I think we have evidence to say most likely if you have an NMDA receptor antagonist that doesn't have some like really unique subtype selectivity that we don't know about yet, that it's going to have to probably be used at dissociative doses to achieve the same level of inhibition that you get with ketamine. Again, unless it's mechanistically diverse. So someday we might find, you know, NR2C, 2B heterotrimers don't cause dissociative effects, and that underlies the antidepressant. That's fine, but we don't have those drugs yet to test. So the drugs we are testing aren't very specific, and they seem to all cause dissociative effect. The other problem is kind of what I was hinting at with, you know, there's some studies which claim dissociative effects don't correlate with the antidepressant effects. The problem there is their rating scales that they're using, and also the doses. You could easily do two studies, right? One where you show dose does correlate with dissociative effects, another where you show it doesn't. And the easy way to do that is if you pick like a low, medium, you know, like threshold and then high dose, you will show a correlation between, like without question, ketamine's dissociative effects correlate with the antidepressant effect because you can't achieve the antidepressant effects without causing dissociation. But if you pick a narrow dose range, 0.4, 0.5, 0.6, well, yeah, then it might not correlate with the scales because you're like in the weeds looking at a very narrow measure on a rating scale that we haven't even validated to begin with. So.
Any other questions? Lady at the back there.
To what extent the side effects of ketamine can be attributed to on or off target effects, and therefore in the drug discovery initiatives, is there scope to design these out without losing the primary purpose of the drug?
Yeah, it's kind of the question about kind of pharmacological specificity of ketamine. So people often call ketamine a dirty drug, but in fact, it's quite selective if you look at physiologically relevant concentrations, as far as we know. About 2 orders of magnitude selectivity. The next interactions you see 100-fold lower, right? You need 100-fold higher dose, or at mu, kappa, some of the monoamine transporters, sigma receptors. I suspect those are not involved directly until you're at like anesthetic level dosing, where you're reaching 10, 20 micromolar concentrations in the brain. You know, so, and then even then, how relevant is that? I don't know.
I think we have time for one more question.
It's a quick two-part question, though, or comment. First, with the linesamine, if you look at those 2 studies back to back, the actual drug effect was completely identical. The only thing that changed was the placebo effect. So it gets me to the second point is, how do we know, well, and I'll ask you one other bit, all the Janssen data really doesn't show a correlation between the dissociative effect and clinical response with anything except for the first dose, maybe. So the question is, how do we know it's just not the functional unblinding that the dissociative effect is providing?
Yeah.
And the rest of it is, there probably has a real effect, but what makes it statistically so prevalent is that you get this functional unblinding.
Yeah, so to be clear, I'm not saying that dissociation is like necessary and correlates in like a linear sense. I'm using it more as a yes/no thing. Are you getting target engagement? And that's true. I mean, you feel intoxicated at the doses of ketamine that are active, without question. Again, whether the rating scale shows that or not, it's a problem with the rating scale. If you take 30 milligrams of S-ketamine, it feels like several beers. I call that dissociation. So I think that's kind of like where I would say it's like a more qualitative thing, not quantitative, maybe.
I agree. I mean, with your overall premise, I agree with. I think what you're saying is correct. But the other thing is, not every test with Glycine showed. There were some that didn't. So, for example, glutamate release, either by microdialysis or by C13 imaging, nobody was ever able to show that Glycine or Repastinel was able to do that.
Yeah, and that's interesting. It probably is because the level of inhibition wasn't sufficient to drive that. But yeah, I just mean more in the sense of the narrative that was presented was very sort of favorable. But to the point about unblinding, I think is a good one. And that's been pointed out with SSRIs, and any side effect you can say, patients can sometimes realize they've been given the drug. And my argument to that is like, well, who cares, right? Like, if that's what's driving the improvement, does it actually matter?
No, I guess the thing is, that's not what's driving the improvement. That's what makes it really difficult to detect the difference in improvement. Because that first linesamine study, patients really didn't know so much what was going on. It was a nice separation. After that, there was much more hype about it. All of a sudden, everybody got better.
Yeah, but I mean, with respect to like the dissociative effect unblinding, if that is what is doing the improvement, the dissociative effect is a pharmacological effect of that drug. So just because the improvement is from a psychologically induced effect versus an inactive placebo, I've always found that kind of an interesting.
But that's not the point.
No, I get it about linansamine. Yeah.
If you don't have that, it makes it harder to separate the two.
Yeah, just a technical.
Yeah, no, I get.
I think we probably, this is great. It could go on for a long time, but we should probably move on. So thank you very much, Jason.